In Chapter 5, we'll be looking at binomial distribution. And a binomial distribution is one of the two types of distributions that we're going to focus on. In Chapter 1, we talked about how to get a sample. And in 2 and 3, we talked about different ways to organize and present that data, like, for example, when we pretended to roll that die 100 times. In Chapter 4, we took our probability, given our experimental data, what is the probability that, I'll roll a 2 or that I'll roll a 5, what does that distribution look like? And then also the theoreticals. If I were to roll forever, what would be the probability of rolling a 2? We're going to take those two ideas now and merge them together so that we can look at how the theoretical model describes the experiment so that you kind of know what to expect to happen. And so the idea is throughout the whole course that we're taking samples and gathering stats, and then we're going to use those stats to make some inferences, to make some decisions, to make some statements about what happens in the overall population and if you had the everything. We'll talk about the random variable x. That's kind of our magic number. You'll kind of think of variable x as your r from when you were doing combinations and permutations. We'll look at two different types of probability distributions, but one important thing to remember is that their histograms will give all of the probabilities underneath that curve. So everything that could happen will be represented on the histogram, and it will be a relative frequency histogram, right? So we're going to be talking about a lot of probabilities, not frequencies, not how many times did it happen, but what percentage of the time did it happen. And everything under the curve has to add up to a 1. So when you add up all the probabilities that are under that curve, it has to be equal to the 1. Now, the individual x's are going to be somewhere between 0 and 1. Probably none of them 1, probably none of them 0, although they'll be so close to 0, we'll consider them trivial amounts, and we'll just say, your 0.000005 is 0. Our most popular formula that we'll use is the one for mu. So the mean, where you take all of your x's, you multiply them by your probabilities, and then you add them up. Very similar to what you did when you were finding a mean of a frequency table, right? When you were given the classes and then you had to find the class midpoint. You do not need to divide here. The weighting is taken care of because we're using probabilities and not hard counts. The variance formula, it's a alleged shortcut. And the square root formula, we're not ever going to do by hand. We'll use our calculator for that. We can still use 1 vars. And it also gives you the mean as well. But sometimes to find the mean by hand is actually faster than putting it all into your calculator. The same rule of being within 2 standard deviations applies. So if you're 2 up or 2 down, those are your usual values. We're going to kind of assume all these guys are normally distributed, although they're probably not going to be perfectly normally distributed. We'll also tend to call the mean the expected value. And you'll start to see that language in a lot of the example problems that you'll work throughout the homework. So it's not like what's the mean payout, because sometimes we do talk about payouts. It's the expected value of your winnings or the expected value of what the insurance company would have to pay out. So mean and expected value are the same thing. We'll use E, which is a little bit unfortunate because E will mean something else later on in the semester. We don't use the E a whole lot for expected value. We tend to just use mu. Binomial probability distribution has to meet 4 requirements, and this is one of the questions on your final. It has to have a fixed number of trials, so you got to stop eventually. You can't roll a die forever. So you can roll a die 100 times, 50 times, whatever it is. The trials have to be independent, so what happens first does not impact what happens afterwards. So this is not a blackjack situation where you're taking cards out. This is more roll a die, or maybe you're flipping a card where you're putting the card back in. The trials have to be classified into 2 categories, and that doesn't mean that there's 2 outcomes. Think of it as what I want and what I don't want. There might be lots of things in the category of what you want and lots of things in the category of what you don't want, but it's kind of a yes-no situation. We'll see a lot of yes-no, heads, tails, left, right when we do our project. And because the trials are independent, the probability of success, which we're going to call P, remains the same. All right, so if the trials are independent, what happens first doesn't change what happens next. So the probability of me getting whatever it is that I want will remain constant. That's important. So the probability of success is P. The probability of failure or not getting what you want, we're going to call Q. And of course, those guys are disjoint. So what will happen is they'll always pretty much tell you P in one way or another, and you'll have to say 1 minus P to get Q. N's the number of trials. X is the magic number that we're talking about. Those trials have to be somewhere between 0 and N, whole numbers, right? You can't have half of a trial. P, like we said, is probability of success, where Q is failure. P of X is still that probability. A lot of times they don't ask the questions like they did when you're just in a probability unit of a textbook. There'll be more in a sentence form. This is the formula that if you were going to do this by hand, that you would use. We're not going to do this by hand. I'll show you an example, but what we're looking at is, here's your combinations, right, that we had from NCR in the other chapter. Probability of success raised to the likelihood of how many times something I want can come out. Failure, N minus that, so number of trials minus the number of times that it came out, from 0 up till however many trials there are. So an example would be your planting pea pods, and the probability of a pea pod of having a green pod is a 0.75. This is going to be our probability of success, right? That the pod is green. Use the binomial formula to generate the probability of getting exactly 3 peas with green pods when you plant 5 offspring. So I plant 5 little pea pods. What's the probability that exactly 3, and the exactly is an important idea. So I want to find P of 3. N's 5, X is 3, kind of like our R, right? Imagine you had 5, pick 3 of them that you want them to be green. P is 0.75, so that means 1 minus that is Q, or 0.25. You would plug that into your lovely formula and then break out your calculator to crunch this number, and you would get 0.263 and some change. And so about 26-ish% chance of getting exactly 3 pods, which seems a little odd, right? So your probability of success was 75%. You would think, well, I have a 75% chance of getting the green pea pods. Let's look at another example, and we'll talk a little bit about why that's so strange. McDonald's brand recognition, 95% recognition rate. Everybody knows the golden arches, right? So you go around and you select 5 people, just like we did before, and we want to know the probability of exactly 3 people knowing that that is the McDonald's symbol. So we're not going to do this in the calculator. We're going to do this in the calculator, not by hand. You go to second vars to pull up the distribution menu, and you scroll all the way down till you see binomial PDF, probability density function. The CDF is cumulative density function. I tend not to use that a whole lot, and we'll talk about why in a couple of minutes. So you're going to hit enter on the binomial PDF, and then you'll see number of trials, P, and the R value or the X value that you're looking for. So trials was 5, probability of success was 0.95. I'm looking for exactly 3. When you hit enter twice, you get 0.02 and a little bit more. So about 2% chance. That's really peculiar, right? Because we just said you had a 95% chance. You talk to people and you want to know exactly 3. See, that's the problem, that you want to know exactly 3. In all likelihood, more people would know. So for letter B, where it says, find the probability of the number of people who recognize McDonald's is 3 or fewer. I would do the same thing as I did before, but I would not put the X in at the end. So when you put the X in at the end, it's going to look just like this. You hit enter, and this pops up, this second line in here. And you can scroll through that, but it's going to be a little messy. So instead I hit store, which is an arrow key down towards the bottom. It looks like this arrow key right here. And then second 2 to put it in list 2. When you hit enter, it just kind of looks like it does it again. But now, when you go to stat edit, you'll see in your L2 all of these values. What you'll want to do is scoot over to L1 and start at 0 and start counting your way up. So you're always going to have one more probability than the number of trials because you have to account for the 0. So the probability that nobody recognizes the golden arches is 3.1 e to the negative 7. Be on the lookout for your scientific notation. That says take your decimal point that you have right in between the 3 and 1 and go 7 places back to the right. So it would be 0.0000003, basically 0. For 1, it would be take that decimal point, which is right after the 3, 5 places back, so it would be 0.00003. We'll still go ahead and call that a 0. And then the 2, 3, 4, and 5 are pretty easy to see. So if I want to know 3 or fewer, I can say, well, here's my probability for 3. Here's my probability for the 2. This was really a 0, and this was really a 0. So I'll just go ahead and add these two guys up. And the probability that my x is 3 or fewer is going to be 0.2256, and you round to wherever they want you to round. Usually it's 4 decimal places, so probably 0.0226. Right? And that kind of makes sense, because the fact that you didn't know it is going to be unusual. So to find only one person that knows what the golden arches are, or 2, is unusual. So what about 3 or more? Same thing, and you wouldn't have to run it again, but now it would start here and add up. And you can see you have a much higher chance of everybody recognizing it, right? 77% chance. So 3 plus the 4 plus the 5, right? Because if I want 3 or more, that's 3 or 4 or 5. And when you say or, you add those probabilities. So you have a much higher chance, almost 100% chance, right, that 3 or more people would know them. So if you want to know an exactly, you put a number in over here. If it doesn't say exactly, so it says 3 or more, or at least 3, or less than 2, or 2 or less than that, or that's when you leave that off. And we're going to stop here. We'll look at the specific formulas for how to use the NPs and Qs when you don't have a storyline later on.